Hello, so for this video, I brought with me this science toy, but it's a really cool toy because it explains by demonstration how Lenze's law works. Now, Lenze's law is about an effect that occurs when you move something in a magnetic field and therefore generate electricity in the conducting material that is moving relative to the magnetic field. And that conducting material, because of the electric current, produces its own magnetic field. And it turns out that when you have the conducting thing have a magnetic field, that allows it to interact with the external magnetic field, which induced the current to begin with. So here we have, I think this is just aluminium. It feels fairly lightweight metal. And inside this, we have a coil, a densely packed coil of wire, probably copper wire. It's worth saying this wire is usually not magnetic. Here I have quite a strong magnet. Now I won't be doing this video too close to the screen because this is a fairly strong magnet, but one can kind of see that this isn't magnetic because it's not, it's not sticking to this at all. It's just, essentially, if this is in contact with this for a very short time, such that the motion of this cannot generate current in this coil, one can clearly see that this coil is usually not magnetic. However, if the magnetic field that this is generating remains in the vicinity of this long enough to produce a current which has an observable effect, we can see Lenze's law in action. So, when I drop this through this, bearing in mind, I think that was just the wind closing the door just there, nothing to do with Lenze's law, but if we've got, this core, bear in mind this core is not magnetic, and if I drop this normally, it falls quite quickly. But if I drop this through here, try and make sure the camera can see it, then it takes ages to fall. You can kind of see it falling out the bottom. It does so very, very slowly compared to, its usual speed. I'll see if I can drop it through at an angle so one can see it, you can kind of see it there. It's worth saying there's very little friction, so it moving slowly is solely really due to Lenze's law. It moves incredibly slowly through this. I might be able to tilt the camera, so vertigo warning, I'm going to try tilting the camera and showing this in motion. So you can hopefully see it like that. I mean, I have to be careful to catch it, but you can hopefully see it move through at a much slower rate than it usually does. And that's because when this is moving in this coil, if this coil is stationary, then by definition, this coil is moving relative to that magnetic field. So we have relative motion between a magnetic field and a conductor. And that creates, as I say, current in the conductor, and that current allows the conductor to act essentially like a magnet, providing that conductor is in motion relative to an external magnetic field. Now, there's two possibilities if we're thinking about the effect that this could produce on the main magnet. One effect is that the magnetic field generated here attracts this magnet. in which case it will cause this magnet to accelerate. However, it's worth saying this magnet accelerating would then be a way of giving this magnet energy. So we would violate the conservation of energy. So what actually happens is the magnetic field generated in this, when it moves relative to that, the magnetic field in this repels this magnetic field. And that means that this magnet slows down, or at least experiences a repulsive force reducing its acceleration due to gravity. And because this slows down, it's indicating that some of the gravitational potential energy that it's losing isn't just being transferred into kinetic energy, it's being transferred into another kind of energy. And the other kind of energy is the kinetic energy of the electrons in the conductor. So essentially, as this magnet moves relative to this coil, this magnet transfers some of its, if you like, gravitational potential energy into the kinetic energy for the electrons in this wire, in this coil. So, it's worth bringing up Lenze's law because it's a cool effect. It allows you to slow down, or in some cases, drastically slow down the motion of magnets. That can be used to move magnetic materials safely, because essentially it prevents them reaching too high speeds, because of this repulsive force between the original magnetic field and the induced magnetic field. But also, one can predict whether this magnet will be attracted or repelled by this induced magnetic field, just in terms of the conservation of energy. So the fact that the magnetic field induced in this repels this can be predicted just from the conservation of energy. Now, why we get a magnetic field in this tool, as in why this moving magnet causes the electrons in this copper wire to move, a proper explanation is really due to relativity. But if you've seen things like the motor equation before, or things like that, you'll know that a charged particle, such as an electron, will experience a magnetic force if it is moving relative to that magnetic field. Now, often this is done in the context of particle accelerators, where you have a relatively static magnetic field, for example, and that's simplifying things a bit, because the way particle accelerators are designed, it tends not to be static. But for simplification, you can imagine a static magnetic field, and the charged particles are moving relative to that field. However, we can reverse the situation. We can go, well, that's how the magnetic field moving, but the charged particles be stationary. Well, if that's the case, the charged particles, the electrons in this copper wire, are still moving relative to the magnetic field as the magnet falls through. And that way the electrons in this copper wire do experience a force, and that causes the electrons to move. Now, you might wonder, why does a charged particle have to be moving for it to experience a magnetic field? And that's essentially because a magnetic field is a relativistic shift of an electric field. So to experience a magnetic field, in other words, for the magnetic field to actually exist in your reference frame, you need to be moving relative to it. That's a bit fuzzy, but but that's the broad idea. So I thought I'd do this video to introduce this cool toy. It's only a 10-minute video. I apologise if there's been noises with door banging. Also, at one point, this magnet managed to attract a metal spoon in a pot of salt. But I probably best pause this video before this magnet starts flying around or doing anything else. But anyway, thought it was a cool experiment show, and I'm wishing you a very good weekend ahead. Keep up the scientific research, and exploring the wonderful universe, and I look forward to seeing you for some more wonderful physics soon.